Hello and welcome to the worksheet 10 video key. All right, on worksheet 10, we are still working on stereochemistry, and we talk about enantiomers and diastereomers in this section. And so one thing to note, right, is that if this molecule was to look into a mirror, right, and that mirror was right here, then this would be its reflection. So one thing that we can automatically predict is that the configuration of the same stereocenters will be opposite. So since this one with the fluorine is S, that means that this one is R. With the hydroxyl S, so this one is also R. And with the thiol, R, and so this one is S. Right? And this is really going to be identical to this one because this is essentially just take this and flip it over. Right? Remember that whatever is coming out at you on a wedge, right, is going to be pointed back when you flip it over. These are actually identical compounds. I can go ahead and label this as SRR, identical to what we have here at the same carbons. So now let's consider the following here, right? What we see is that this configuration is the same as this one. So since we have R here, this is also going to be R, right? And that this one is opposite, right? So S will become R. So how are these related? We actually will call these diastereomers, right? Because they have the same number of atoms, same bond connectivities. They only differ in the spatial orientation, but they are not enantiomers because they are not mirror images of each other. So they are therefore diastereomers. We can use this little flow chart to help us figure out whether the relationship between two compounds. First, we would ask ourselves, do they have the same chemical or molecular formula? If you say no, then they have no relationship. If yes, then they are isomers. And of course, they need to be non-identical compounds in some way. And then if they are non-identical compounds with the same chemical formula, we'll ask ourselves, do they have the same atom connectivity from one end to the other? If you say no, then they're constitutional isomers. Yes means that they're stereoisomers. And then if they're stereoisomers, ask yourself, are those two things related as mirror images? The answer is yes, they're enantiomers. If no, then they are diastereomers. So let's practice by determining the relationship between two compounds below. And if you struggle with this, it may help you to designate the configuration, meaning the R and S configuration at each chiral center. So with this, we can automatically tell that while there's two carbons, one oxygen, and same thing here, two carbons, one oxygen, clearly they're not connected with the same atom connectivity. Since there aren't any pi bonds, I know they have the same HDI, so I already know that they have the same molecular formula. Then these are related as constitutional isomers. All right, what about these two compounds that are drawn in Fischer projection? So if you recall from the lecture video, it talks about how when molecules are drawn in a Fischer projection, it's relatively easy to determine their relative relationship. We can see that this chiral center is the same as this one. And this chiral center is the opposite of this one because we've switched the hydroxyl group and the hydrogen to the opposite side. So with one same and one opposite, these will be related as diastereomers. And then lastly, we have molecules drawn with the same relative orientation, right? But looking at the configuration of the chiral centers, we have the opposite configuration and the opposite configuration. And because on one side it's ethyl and methyl, there's no possibility for an internal plane of symmetry. So then I know these are related as enantiomers. If it was possible that there could be an internal plane of symmetry, I would want to figure that out because if the compounds were meso compounds, then they would in fact be identical instead of enantiomers. Let's go ahead and designate the configuration of the chiral centers in case you struggled with this and want to use that as a strategy to help. So for this structure, we have the oxygen, carbon, hydrogen, carbon. So oxygen, 2 carbons are a tie, but this one will have a higher priority. So we go from 1 to 2 to 3, ignoring 4. And then we think to ourselves, well, that 4th priority group is coming out at me. So while it looks like it's counterclockwise in S, it's actually going to be clockwise in R. This one will have this as the highest priority. If you do the analysis, right, this carbon with an oxygen, carbon, and hydrogen versus an oxygen, hydrogen, and hydrogen will have the 2nd highest priority, and then the 3rd. So 1 to 2 to 3, right? And our 4th priority group is again pointing out at us. So what's clockwise turns to counterclockwise, and this is S. Remember that diastereomers should have 1 or more configurations the same or identical, and the other 1 or more opposite. So if we do the same analysis over here, we've got 1, 2, 3, 1. Okay, I should have done this in red. 1 to 2 to 3. Again, clockwise, but the hydrogen is coming out at us, so this is really counterclockwise in S. And then on the top here, we have 1 to 2 to 3. Now this is clockwise again, but hydrogen is coming out at us, so it is also counterclockwise in S. You can see that 1 is the same, 1 is opposite, then you'll have diastereomers. What about over here? Right, let's go ahead and assign priorities. We have oxygen, hydrogen coming out at you, carbon, carbon. This carbon will have the tiebreaker over this one. So 1 to 2 to 3. Again, that 4th priority group is coming out at us, right? So you can even draw that in if you want, or it's a little small, so I'll just leave it off. So again, if it's coming out at you, we're really going to change this counterclockwise to clockwise, and this will be R. And then coming over here, we'll have the same counterclockwise, but again, now the hydrogen is pointing back. So this is really S. And then 1 to 2 to 3, the hydrogen pointing back, this is S. 1 to 2 to 3, the hydrogen pointing out at us, this will be R. So notice how we went from RS to SR, exact opposite at every chiral center, so we have enantiomers. Looking at the next question here, we have more practicing what is the relationship between the following molecules. There might be no relationship, constitutional isomers, enantiomers, diastereomers, or perhaps they're identical. So let's go ahead and look at this one. I always like to show people how they might be able to do it without identifying the configuration first, just by manipulating one of the molecules. So maybe if you can imagine taking this one and flipping it over, right, like flipping it like a pancake. If you do that, the ethyl will rotate down here to where this ethyl is. The methyl will rotate down here to where this methyl is. Remember that these will switch, right, because we're flipping it over. So the fluorine will come out at us and the hydrogen will go back, which is exactly what we have here. These are actually identical. And I can tell that by just flipping this over like a pancake and then superimposing it on this one in my mind. But if I want to double check, I can do that with the R and S configuration. So I've got fluorine, ethyl, methyl as my priority, 1 to 2 to 3. Clockwise with the hydrogen pointing back is R. We can do the same over here, fluorine, ethyl, methyl, so 1 to 2 to 3. This is counterclockwise, but our hydrogen is coming out at us, so it's really clockwise in the right orientation and also R. So same groups, same configuration, they are identical. So these are cis and trans. They have the same molecular formula. So they are a type of isomer. They have the same atom connectivity, so they are not constitutional isomers, but they differ in the spatial arrangement, so they are a type of stereoisomer. They are not related as mirror images, so therefore they are diastereomers. We can see that they've made a point of showing us that these two compounds have the same molecular formula, but we can see that the atoms are connected in a different way because of where the pi bond is, and the hydrogen here has been moved to the oxygen. So then these are related as constitutional isomers. And then just a quick look here shows us that this configuration is the same as this one, but these are opposites. So these will be related as diastereomers. Again, you can do the configuration, the R and S designation, if that helps. You should get the same thing for this one and opposites for that one. Let's move on to enantiopurity. So how pure a substance is in one enantiomer over the other is expressed as the percent EE, also known as the percent enantiomeric excess. Let's consider the following scenario with compound A being this yellow color, compound B being represented by the blue color. And then we have 5 different percent compositions, and they are 100% yellow, 100% blue, 50-50, 90-10, 10-90, and 75-25. So we're being asked to write in what the percent EE would be for each of these mixtures and the observed rotation, given that we know the optical rotation or the specific rotation of the pure enantiomer, or both pure enantiomers, in fact, but you really only needed one because you know the enantiomer then will be the opposite direction as its enantiomer. Okay, so in terms of percent enantiomeric excess, we have 100 and 0. So we would have 100%. And then we also would have, in the second case, 100%, but the opposite enantiomer. This is 50-50, right? So the percent enantiomeric excess would actually be 0, right? 90-10. So we would take 90, subtract 10, and we would get 80%. Take the other 90 and subtract 10, and we get 80%. So we just take the larger number, subtract the smaller number to get the percent EE. And 75-25 is what I said for this one. So 75 minus 25 is 50% EE. So based on this, we can take a look at what the observed rotation would be. So we have 100% A and 0% B in the first case. So we would get a rotation of plus 100 degrees. With 100% blue would be negative 100 degrees. 50-50 would be 0 degrees. 90-10 would be an 80% enantiomeric excess, and the blue one would be in excess. It would be negative 80. If the excess was 80% in A, it should be positive 80. And then 50% excess, right, where the excess is the blue one, would be negative 50. Okay, so remember the equation for calculating optical purity or percent enantiomeric excess is the absolute value of the specific rotation of the sample mixture divided by the absolute value of the specific rotation of one of the pure enantiomers times 100%. Let's use that information to answer the next question. And it says a mixture of A and B above gave an optical rotation of plus 4.00 degrees. How much of each of the enantiomer is present? So before we can answer that, it wants us to take a look and answer question A, or part A, which is, since the optical rotation of the mixture is plus 4 degrees, do you have more of A or B? Right, so if we'll go back to looking at what we had here, right, remember that we had more plus because it was plus 4 degrees, so we have more A. Right. More A because plus 4 matches plus 100. So pure A enantiomer. Right? Plus and plus. Okay. Since your observed optical rotation is only 4, which is a lot less than plus 100, do you have a lot or a little in excess of one enantiomer over the other? So 4 is not very much compared to 100, right? So we would say a little, because plus 4 is only 4% of 100. And then now it says calculate the optical purity. Remember, we're going to use that equation that we saw on the last page. So that equation was percent EE, or also known as optical purity, is equal to the absolute value of the specific rotation of the sample mixture divided by the absolute value of the specific rotation of the pure enantiomer. Times 100 equals, right? So putting those values in, we have the absolute value of plus 4, which of course is already plus, so we didn't really need an absolute value, but if it had been negative, we would turn it positive, divided by plus or minus 100 times 100 is 4%. So we have 4% enantiomeric excess, right? So that is not very much excess compared to 100%, right? So what we can do in order to figure out how much of A we have and how much of B we have in solution, right, is we have so excess, right? We know we had excess A, so we have our 4% A, and then 100 minus the percent EE is equal to 96%. We're going to split this in half to, let's see, 48 and 48. Right, and that will be 48% A and 48%. So total, we have 52% A and 48% B. We really only have a small excess of A compared to B. Okay, moving on to question 12. What is the percent EE of a sample of carbon that exhibits a specific rotation of -40 degrees, given that the specific rotation of our carbon is -61. So percent EE will be equal to the absolute value of -40 divided by the absolute value of -61 times 100. We have to use our calculator, unless we're really good at math. And we have 40 divided by 61 equals, and I have 65.57, two significant figures here, so 66% EE. So that was what we asked. It didn't ask us how much of each enantiomer we have, right? But if we wanted to, we could answer that question, as the mixture is rotating in the lever rotatory direction, and so is our carbon. So we know we have more R carbon than S carbon, specifically 66% more. So the other amount, 100 minus 66, would be 34. 34 divided by 2 is 17. So we'd have 17% S and 80, I do this math in my head, 83% R. It didn't ask us to do that though, so I'll just leave it off of the answer key. And then last question number 13, explain why the stereoisomer A of tartaric acid has 0 optical rotation. So we notice that this stereoisomer, which has an RR configuration, is rotating positive 24.8 degrees. Its enantiomer is rotating negative 24.8 degrees, but this one rotates 0. And notice how it has opposite configurations with the same groups attached at each configuration. So if we were to actually flip this, sort of take half of the molecule, right, or rotate this central carbon-carbon bond, we'll be able to draw it in a way where we can find an internal plane of symmetry. So we can view it. Remember, if I take this and I flip it over, what's going back is now coming out at me. And now I can see there's an internal symmetry. Right, so this is a meso compound, which means it's achiral, right? And it's expected to have no optical activity, which explains why it is measured at 0 degrees. Moving on to the next question here. We have, it says, consider some of the 16 different stereoisomers of the following sugar. You can see this is the most common one, D-glucose, but there's also other ones. This is D-glucose, like D-mannose, glucose, ultrose, allose, and also D-L. You may, by looking at the structures, you may have figured out why some are called D and L, but if not, it's actually this final chiral center. And if we have the OH group on the right, we call it D, and the OH group on the left of just this last chiral center will always be called L. So that's where that D and L comes from. Okay, so we're asked to, what is the relationship between D-allose and L-allose? Those are these first two here. You can see that the hydroxyl groups are all on the right versus all on the left in this compound, right? And so these are related as enantiomers. And they have opposite optical rotations. The next question says, what is the relationship between D-allose and D-ultrose? right? And so we can see here that the last three stereocenters are the same, but this top one is different, right? So these would be related as diastereomers. And compare their optical rotations of plus 14 and plus 33. So there is, we'll just say there's no predictable relationship in their optical rotations. So with diastereomers, we can't know or predict the different optical rotations. As you can see, it could even be the same. Right? Look at these two that are related as diastereomers, and they actually even have the same optical rotation. So we can't even predict that they'll be different. We just have no idea what it will be with diastereomers. Okay, the molecule D-maltose shown below is another stereoisomer of allose. Comment on its optical rotation. Right? So we basically have no idea. We cannot comment other than to say the optical rotation of D-maltose cannot be predicted and must be measured experimentally. I could predict it if I knew what L-maltose was, but that's not one of these options, so I don't have any idea what it is. Because remember, there is no correlation between the stereochemistry in a compound and its direction or magnitude in terms of its optical activity. So some notes on optical rotation. Enantiomers have, I might say opposite, observed optical rotation. A racemic sample has no observed optical rotation. And an achiral or non-chiral compound would also have no observed optical rotation. And diastereomers have optical rotations that are not predictable. I guess that would be the best definition there. Okay, I guess we'll just leave it at not predictable. All right, so let's stop there and hope you guys have a good rest of your day.